Let's begin section 3.1, Systems of Equations. First, let's recall what we know about linear functions and linear equations. We had that y equals mx plus b. This is an equation that we can interpret as a function. Now, let's look at it as an equation of a more general form. That being a linear equation of two unknowns. We'll represent this with ax plus by equals c. And note, we might be reusing a letter, but of this form, this b is not referring to y-intercept anymore. And let's include a definition. We say that a solution of an equation is a pair of values that satisfy the equation. And by satisfy, I mean when we plug it in, the expression is true. So as an example, we have the general linear equation of two unknowns, 5x plus 3y equals 2. Negative 2, 4, which is to say x equal negative 2, y equals 4 is a solution because 5 times negative 2 plus 3 times 4 equals 2. Now to be certain, we would want to check this. 5 times negative 2 is negative 10. 3 times 4 is 12. And yes, negative 10 plus 12 is 2. A non-example would be 1, 2 is not a solution. This is because 5 times 1 plus 3 times 2. Again, this is 5 plus 6 equals 11, which is not 2. It can be important to note that solutions are not always unique. And in fact, if we're looking at the solution of a single linear equation of two unknowns, we will frequently get infinite number of solutions, and that's all of the points that lie on that graphed line. Because the graph of a function is the same as the solution set of solutions, and that means we already know how to plot the solution set. Which is good. As an example, we could be asked to graph the solution set, or the set of all of the solutions of two linear equations of two unknowns. To make these two equations look familiar, we can rearrange them. 5x plus 2y equals 4 is the same as 2y equals negative 5x plus 4, which is y equals negative 5 halves x plus 2. Similarly, x minus 2y equals 2 gives us negative 2y equals negative x plus 2. Y equals 1/2 x minus 1. Let's graph our first line. Its y-intercept is at 2. And its slope, it rises negative 5 as it runs 2. So it goes down 1, 2, 3, 4, 5, and over 1, 2. Our next line has y-intercept at negative 1, and it rises 1, and it goes over 1, 2. To have a slope of 1/2. Here we see that there is a point where these two solution sets intersect, meaning there's a solution that is common to both of these equations. This point is 1, negative 0.5. My graph might be a little imperfect. Is a solution to both 5x plus 2y equals 4 and to x minus 2y equals 2. For this reason, we say that 1, negative 0.5 is a solution to the system of linear equations of two unknowns, 5x plus 2y equals 4. A system of two equations of two unknowns has the following form. Incomplete generality. Where A, B, C, D, E, and F are numbers, and they're not necessarily all different. A solution to a system is a solution to each equation in the system. We can think of it as the point where the two lines intersect. And although we found it graphically before, and although we can think of it graphically, we can also find it algebraically. By symbolic manipulation. Let's see an example. We could have 5x plus 2y equals 4, and x minus 2y equals 2. We'll explore many ways to solve a system or to find the solution of a system, but for now, let's use the fact that if we have two statements of equality, we can add both sides to each other and we would still have equality. What that means is we could add 5x plus 2y plus x minus 2y, and on the right hand side we'd have 4 plus 2, and these things would still be equal. The idea being, if we can find certain combinations of adding the R2 equations, one of our variables may cancel out. In this case, the y would cancel out, and we'd be left with 6x equals 6, telling us that x equals 1. At this point, we could look to either our two equations. Let's use the first one and say if 5x plus 2y equals 4 and x equals 1, then we would know that 5 times 1 plus 2y equals 4, that 2y equals 4 minus 5, which is negative 1, and that y equals -2, -1/2, giving us the solution x equals 1, y equals -1/2. Let's do another example. So let's have our first equation be 3x plus 2y equals 1, and our second be 6x minus 5y equals 5. Now we can imagine if we tried to do what we did last time of just adding the two equations together, we would not have one of the variables cancel out. However, I notice that our coefficients on the x variables happen to be multiples of each other. Since I know that 3 times 2 is 6, and I want them to be opposite so that when I add them they cancel out, I'm going to multiply the first row by -2, which means I would have to multiply that right-hand side by -2 as well, and add the second row. This would give us -6x minus 4y plus 6x minus 5y equals -2 plus 5, which is 3. Here we have our 6's cancels as we would like, and we're left with -9y equals 3, or that y equals -1/3. Once we've solved for one of our variables, we can then choose to plug in our y equals -1/3 to either of our equations. Let's use the first. We would have 3x plus 2 times -1/3 equals 1, and 3x plus -2/3 equals 1, 3x equals 1 plus 2/3, which equals 5/3. So x equals 5/3 divided by 3, which is 5/9. Which tells us that our solution is, I'll give it as an ordered pair this time, 5/9, comma, -1/3. When thinking about the solution set of two equations, let's ask another question. Do two lines always intersect? The answer, of course, is no. And because the solution set of a linear equation can be thought of the same as the graph of the function, and because the graphs of these linear equations are lines that might not always intersect, not all systems have a solution. If a system has no solutions, it has a special name. We call it inconsistent. I claim that the system 2x plus y equals 4 and 4x plus 2y equals negative 3 is inconsistent. Sure enough, let's look at this in two different ways. 2x plus y equals negative or equals positive 4 can be rearranged to say that y equals negative 2x plus 4. Just like 4x plus 2y equals negative 3 can be arranged into y equals negative 2x minus 3/2. Here, that same slope tells us that they're parallel, which tells us that there's no solution. There's no point where those parallel lines intersect. How else can we see that this is inconsistent? Well, let's take negative 2 times equation 1 plus equation 2. This might be a slight abuse of notation, but what I mean it to be is negative 2 times 2x plus y plus 4x plus 2y is equal to our negative 2 times 4 plus negative 3. If we were to continue this, we would get negative 4x minus 2y plus 4x plus 2y equals negative 8 minus 3. On this left-hand side, the x's cancel, however the y's cancel as well, leaving us with 0 on the left and negative 11 on the right. But 0 does not equal negative 11. Because that statement is not true, or because the statement 0 equals negative 11 is not true, no solution. So that's two ways that we can see when a system is inconsistent. There might also be infinite solution. Here we call this systems redundant. You might ask the question, when do two straight lines intersect each other an infinitely many number of times? Well, that only happens when we're actually talking about the same line. And if we're actually talking about the same line, then we don't need two separate equations. Thus, the two that we're given are redundant. We can see that in this example of a system 2x plus y equals 4 and 4x plus 2y equals 8. It's redundant. It has infinitely many solutions. How do we know? Well, we could try to use our similar methods canceling out. If we multiply this top row by -2 and add it to our second, we get -2 times 2x plus 4x is 0x. -2y plus 2y is 0y. -2 times 4 is -8 plus 8 is 0. 0 equals 0 is true. It's true, but it doesn't tell you anything. And although we might have infinite solutions, we can still describe its infinitely many solutions. And we can describe it as y equals -2x plus 4. Where did this come from? This y equals -2x plus 4 is what we would get if we rearranged either of our equations into that y equals form. On WebAssign, such a solution might be asked to be inputted in the form of x, comma, -2x plus 4. Here the x is saying whatever x is, here the y is whatever y is, but note we know that y equals -2x plus 4, so we can just write this equivalent statement of y as -2x plus 4. Let's do an example. In a past Brexit deal vote, there were 230 more votes against than for. We're also told that there were 634 votes cast. Our question might be, how many voted for? How many voted against? To begin, let's assign some variables on what the things we're looking for. We're asked to find how many voted for and how many voted against. So our variables should reflect that. Let F stand for number 4, and let A stand for number against. Next, we need to interpret our data and see if we can construct any equations. We're told that there were 230 more votes against than for. So we know that against is the larger number. There were more votes for against than there were for. So A is the bigger one, and if we took away all the for, we'd still be left with 230 votes. We're also told that 634 votes in total were cast. As an equation, that means all of the against and all of the for came to a total of 634. Now let's try to combine such that we cancel out a variable. Here I see a positive f and a negative f. Which means I might be able to just add these two things together. A plus A gives me 2 A's. Negative f plus positive f gives me 0 f's. And 230 plus 634 gives me 864. This means that A, the number of votes against, must be 432. Let's take either of our equations. I'll say A plus F equals 634, and let's plug in what we know, that A equals 432, to get that 432 plus F equals 634, and that F equals 634 minus 432, which equals 202. Finally, because our question did not ask for F's and A's, let's interpret our solution to say that 432 members voted against and that 202 members voted for. One final example. We could say one batch of cookies requires 3 cups of flour and 1 cup of sugar. And that one batch brownies might require only 1 cup of flour and 2 cups of sugar. If you have 25 cups of flour and 20 cups of sugar, and you want to use up all your ingredients, how many batches of sugar, how many batches of cookies and brownies should be made? Here we'd want to assign variables to the things we're looking for. We're being asked to find a statement about batches of cookies and batches of brownies, so our variable should reflect this. we can use C for the number of batches of cookies and B for number of batches of brownies. Let's interpret our data and ask, where do we see numbers? Well, we see 3 flour, 1 cup of sugar. It should be 3 cups flour. We see somewhere else 1 cup flour, 2 cups of sugar. We also have 25 cups of flour, 25 cups of sugar, and we want to use all of our ingredients. Well, we know then we have 25 cups of flour. And so we might ask, if we want to use up all the flour, how can we use up all the flour? 25 cups should equal however many cups of flour each batch of cookies required. Each batch of cookies required 3 cups of flour. And we should also be considering how many cups of flour each batch of brownies made. Since each batch of brownie required 1 cup of flour, we get the equation 25 equals 3C plus 1B. In a similar fashion, we have 20 cups of sugar. So let's look at how do we use up our sugar. Well, for every batch of cookies, we'll use 1 cup of sugar, and for every batch of brownies, we'll be using 2 cups of sugar. So we have our 2 equations. Just to put it in the form we might be more familiar with seeing, I'll rearrange so that the variables are on the left-hand side. Now let's try to cancel out a variable. I see no reason to try to cancel out one over the other, so I'll just try to cancel out the first one, the C. How can I do so? Well, I should multiply the second row by -3, because -3 times 1 is -3. -3 plus 3 is 0. So -3 times 1 is -3 plus 3 is 0. -3 times 2 is -6. -6 plus 1 is -5b. -3 times 20 is -60. -60 plus 25 is -35. This gives us that b is equal to 7. Let's plug this in. We can use either of our equations. So I'll use maybe our first, 3c plus 1b equals 25. Gives us that 3c plus 7 equals 25. That 3c equals 18, which tells us that c is equal to 6. So our answer we should make 6 batches of cookies and we should make 7 batches of brownies.